In today's lesson, we'll be talking about the reflection across the horizontal axis, the reflection across the vertical y-axis, the reflection across the origin, and reflection across the line y is equal to x. And lastly, I want us to end the lesson by conversion of bases of exponential functions. So let's first begin with let me just write here the reflection. I don't think you can see properly. Let me use this one instead. The reflection across the horizontal x-axis. What do you have to note when it comes to the reflection across the horizontal axis? The first thing that you will notice in this reflection is that if you have a curve above the x-axis, then the reflection of this curve will be below the x-axis. That's what is important. If you have a curve above the axis, so its reflection will actually go below the x-axis. Let me give you an example here. I want us to be as quick as possible when it comes to this particular lesson here, because if we don't, we will end up not have enough time to finish the lesson. Okay, and then this is y and this is x. Suppose that we have this curve here, and this curve here is y is equal to x squared. And now we wanted to find the reflection of this curve across the x-axis or across the horizontal x-axis. So if the mirror was here, I have the mirror here along the x-axis, and now I am standing on this side. Since I am on this side, this is not how it looks like. It should be like something like this. Yeah. If actually I have this curve here and I'm standing on this side, you will find out that what I will see on the mirror as this is coming towards me, on this mirror here, which is along the x-axis, the reflection will look something like this. So we have this curve here, so whenever it is above the x-axis, then it will be below the x-axis. And also another thing to take a look at into this, whenever you have, this is another point to note, whenever you have y is equal to f of x, the reflection across the x-axis is given by, take a note of this here, whenever I have a positive value that is here, when I'm looking into the mirror, if I'm standing here in the mirror, I will have that point here. This was positive, it becomes negative, even though I still have the same value of x here. And also at this value here, it was positive, it becomes negative. If I were to stand on this side and look at this curve, its reflection along the x-axis will be that black curve. So this one actually, it means that now the reflection will be y is equal to minus f of x. So whenever you are seeing a function, some function and a minus in front of it, it means that I had f of x, but now it was reflected about the horizontal x-axis. So that's what is important about this curve over here. I can make another example here. Another example will be, I have a curve which is like this. Now, the reflection of this curve across the x-axis, if there's a y-axis and there's a x-axis, and I'm standing here looking into this mirror, the reflection will be like this here. So we have a reflection across the horizontal x-axis. So in a nutshell, you can see that whenever I have x and y, it is always reflected, and then you will end up having the same x, but y will change its sign. So that's a reflection across the horizontal axis. And this one is also important, so that when you're spotting a function, and this one is also important when you're dealing with a coordinate, and if I give you a curve, this is also important. Now, let's go to the second one. The second one is, we want to talk about the reflection across the vertical y-axis, or just across the y-axis. Now, what are the key points when it comes to the reflection of this? If you have a curve, on the right side of the y-axis, then its reflection, or its reflection will be on the left hand side of the y-axis. So that's what is important here. So if you have a curve on the right side of the y-axis, then its reflection will be on the left. And also similarly, if you have a curve on the left hand side of the y-axis, its reflection will be on the right hand side. That's what is important here. So if, let's say, I give you a curve here, just gonna make an example here, just try and be quick as possible. I give you a curve, these are the y-axis, these are the x-axis. I am giving you this curve here, and I say this is your curve here, and this curve is y is equal to square root of x. Now, if you look into this curve here, and I am saying I want the reflection of this curve about the y-axis, or across the y-axis. Now, what that's supposed to mean, it means you have a mirror along the y-axis. And now that you have that, and you are standing somewhere here, you're standing somewhere there, and now that you are here, you are looking at this. Let me take this image here so that you can properly see. You are standing somewhere here. You're standing somewhere here, right? Now that you are there, you are looking into this curve, and this curve is coming towards you, and you look into this mirror over here, you will see a reflection going that way. And if you look into that curve, you will find out that this function here will be y is equal to the square root of. Take note that whenever you have these values of x, negative and you're plugging them there, you will get an undefined. So this side you will have a minus x, so that whenever you have a minus times the negative number, you get a positive number, then you take a square root. So you will end up having a function of this type. So whenever I give you a curve like this and you're looking for its reflection will be this side about the y-axis, and the reflection of this about the y-axis will become that side. And now another key points will be, whenever you are given a function y is equal to f of x, and now you are looking for the reflection of this curve about the y-axis, it will become y is equal to f of minus x. Can you see that I have changed the sign to get to this side, and also to this side I just changed the sign to get to that side. So the reflection along the y-axis is always shown by this particular sign over there. And to extend this to some of the important topics that we have covered so far, you will find out that if, let's say, I am giving you a function, I have y and x there, and this function is of this type here and also of that type that side, or I can just give you a quadratic. Let's just use a quadratic. Let's use a quadratic because we used it before, and then let's use a quadratic. You have a quadratic function y is equal to x squared there. If you want to find out, if you stand this side, right, and you want to find the reflection of this curve by the y-axis. So if you're standing this side, you will find out this on the mirror, it will become this nice thing over here, right? And this side on the mirror, if you were to stand this side, you will notice that it will become this side here on the mirror. So whenever you have a function of this kind, such that whenever you are taking its reflection along the y-axis, you still get the same function, or one piece of that function can be found by reflecting the other piece along the y-axis, such functions are called even functions, because now I have y is equal to x squared. And now when I'm looking for the reflection across the y-axis, I end up getting y is equal to minus x, and you square it up, I still get the same thing as x squared, which was the original f of x. So in this case here, you will find out this function is called even function. That's what is important about the reflection across the y-axis. We've talked about this. It has nothing to do with even functions or even symmetry. An even function is always have an even symmetry. In other words, if I were to cut this curve here, take this side and place it on top of this side, this part here will overlap on top of that, or it will slip on top of this curve here. So we usually say this function is even, or it has even symmetry. So we talked about this, that so what was on the right, it goes it is reflected, and then it goes to the left for the reflection along the y-axis, and on the left it goes to the right. Now let's talk about the third one. Is very important also, because it is a reflection about the origin. This is not the origin. It is the reflection about the origin. Now, what is a reflection across the origin, and what should you expect from the reflection about the origin. Let's take a look at what we said here. If you have a curve on the left and then it will go on the right, and when we're talking about this, if you have a curve above the axis, it's going to go below the axis. The reflection will go below the axis, and if you have a curve below the axis, will go above the axis. Now let's look at the reflection about the origin. One thing to note is that the reflection about the origin passes through two mirrors. In other words, you have one mirror image, it passes through mirrors, right? I'm saying two mirrors, or it passes through two mirrors. It is two reflections in one. Let me explain what is happening here. Now, the reflection across the origin is like this. First, let me do this. If you are given a curve, right? The first image will be the reflection about the y-axis. So first you're gonna reflect about the y-axis, you get an image, and then you reflect the image. You reflect the first image about the x-axis. So you reflect the first image about the x-axis to get the second image, to get the second and the last image, right, which is the reflection about the origin. Now let's take an example here. An example will be find, or we can either say find, or I can say draw the reflection of the curve y is equal to x squared about the origin, right? The reflection of the curve y about the origin. Now I want us to actually take a look into this. So the first thing I will actually do, of course, this is the solution that I'm planning us to have. So we have this nice solution here. So we want to draw the reflection of y is equal to x squared about the origin. So we end up having this nice curve here, and then we also have this nice curve there. And then I'm going to place this, and then these are the x's, not curves, Cartesian plane. So you have a y here, and then you have an x there. So first of all, I want us to draw this curve like this, and then I want us to draw this curve like this, right? This is y is equal to x squared, and I want the reflection of this by the origin. This is the origin, reflection about the origin. How do I find the reflection of this by the origin? The first thing that I wanted to have, I will place a mirror here along the y-axis, and then I am going to stand here first. So if I'm standing here at this point here, what will I see as an image of this across this mirror here? So if I were to look into this mirror, the image of this side will be that side there. And if I were to stand somewhere there and look at this curve, the image of this side here will be that curve over there. Remember that I need to see this through on the mirror. I also need to see through this on this mirror here. Our first mirror was here. This was mirror 1. Now, if you take a note into this, this is the first reflection across the y-axis. Now I want to place the second mirror along the x-axis here. So this is mirror 2. So if I were to stand somewhere here, for instance, I were to stand there, right? And now I look into this curve, and when I'm looking into this curve here, I look through the mirror and see what will be the image of this curve in the mirror there. So you will find out this in the mirror, it will look something like this. So this curve will be that. And if you look into this curve here, you stand somewhere here and look in the mirror, you will see that this curve will become something like this. So we have a curve that is going this way over here. Now let's go back a little bit. This one here is our final image, right? The final image, or is the reflection of this by the origin. Now if you look into this, you will find out that the first reflection, which is y is equal to minus x squared, is the same as just x squared. That is why they are just overlapping. And now when you're actually looking now at the second mirror, you will find out that the final image will be this one, which is just y is equal to minus x squared. So that's how you actually go through about this. But for this one, you will find out that this is actually saying that some people will think that this every function that you are given, it's just gonna go and point down. No, that's usually not the case. It's because whenever you have y is equal to x squared, this is an even function. So reflecting it by the y-axis is not going to change the function. It's the change we will start to see is when you're reflecting about the x-axis. That's why we end up having this. And this image looks like that of a reflection across the y-axis. It's because this function is even. Now, if let's say now someone might say, what if I start by placing the mirror along the x-axis and then take the mirror along the y-axis? Will that make a difference? So if we were to take an image of this by the horizontal axis, you would get this. But when we are taking the image of this by the y-axis, we're still gonna get the same thing. So it doesn't matter whether you take the y-axis first or the x-axis first, but you have to go through the two mirrors. Let me take another example here to make sure that we get this the right way. Now, suppose that the question is you are given y is equal to square root of x, and now you want to find out what will be the reflection of this function across the origin. So first let's draw this. It will look something like this, right? It's not perfect. This is y is equal to square root x, and now we want the reflection of this curve by the origin. So the first thing that you do, you place your mirror along the y-axis, and then you stand here and you look at this curve. In the mirror, it will look something like this. This is y is equal to square root minus x across the y-axis. So this one here, it is a reflection of that along the y-axis. But when you want to find a reflection across the origin, or about the origin, you have to place a second mirror there. So the second mirror is the one that will actually give us the final answer here. So when I am standing somewhere here and I look into this mirror here and look at the image of this, we'll find out that the image of this will look something like this. So this one here is y is equal to minus the square root of minus x. So when you look into this, this will be the reflection across the origin of this curve here. So in a nutshell, just a take home for this, you can notice that we did the final image was not here like the previous case, because this function here is not an even function. The image of this, we are not only getting this, the image of that was that, and the image of that was this. So the final image across the origin of this is this orange curve here. So the final take home here, I would say, whenever you are given y is equal to f of x, the reflection of this curve about the origin is going to be y is equal to minus f of minus x. That's what will be the case here. And you can notice that if you are given y is equal to x squared, then y is equal to minus x squared is just the same as minus x squared. Hence, we found out that the reflection about the origin and the reflection about the x-axis was the same for this function. It's because this was even, because this minus did not contribute anything. Now, we talked about the reflection about the origin. Now, it's time for us to talk about the very important topic of the day, which is, let me say, for the reflection across the line y is equal to x. So I want us to talk about the reflection across the line is equal to y is equal to x, and what this reflection is actually doing. This reflection is saying interchange x and y. In other words, if you are given some coordinate system, some coordinate on the curve, this will always be this you will end up having a reflection of this point as yx. So that is what is important here. The second thing is, if you have a vertical asymptote, it becomes the horizontal asymptote. And the third one here, okay, let me first explain this in deep details a little bit. If you have a vertical asymptote, let me say, just to add here, if you have a vertical asymptote, you have a vertical asymptote at x is equal to some value a, then it will become a horizontal asymptote at y is equal to a. So this will just interchange, and if you have a horizontal asymptote at y is equal to a, it will become a vertical asymptote at x is equal to a. So we're just switching or interchanging the asymptotes also. The third one, if you have an x intercept at some x is equal to a, some value a, can be 5, it can be 1, can be -1, can be minus 0,5, then the reflection will have a y-intercept at y is equal to a, right? And also if you have a y-intercept at a, then the reflection will have an x-intercept at x is equal to a. That's what is important here. And then the last thing that is important, the reflection of the function y is equal to f of x is called the inverse. The reflection of the function f of s is called the inverse of f, and this inverse of f is written as it's called the inverse and is written as f with a little minus there. That's the inverse of the function f. Sometimes it is the inverse is a function, sometimes it is not a function. And this inverse here, the domain of this original function will become the range of this inverse. The range of this original function will become the domain of this function. So we are also switching the domain and the range for this particular function. Let's take some examples here. As an example, someone might say find the inverse of y is equal to x squared. So the solution for you will be, you know that whenever you have 2 points x and y, the inverse or the reflection about the line y is equal to x, you're gonna end up having y is equal to x. So you interchange these two. So what will actually happen here, I have y and x, so I'm just gonna interchange and end up having x is equal to y squared. So whenever I have a y, I place an x, and whenever I have an x, I place a y there. So that's the inverse of this, and you can also try and make y the subject of the formula, and you end up having plus and minus the square root of x. And of course, because if I have x is equal to 5 here, I will have a square root 5, which is defined, but now I'll have a plus and a minus, so I have two outputs. So this is going to be not a function because I have 5 and y have two values, so which is plus the square root of 5 and the minus 5 at the same time. So this is not a function, but it is the inverse of that. But in pictures, one thing that you would say that whenever you have this y, you have this function here, which was like this side, and also you had something of this kind. This is y is equal to x squared, And now you want to find its inverse. So first you have to draw a line here. This line is y is equal to x, right? It is line y is equal to x. Of course, you place it as a dotted lines for this, because this one here is going to be your mirror. Now, let's take a look into this. If you were to stand here in front of this mirror and you look at this curve here, you will find out that this portion here will look like something of this kind here, and then it's going to pass through that point. And then if you're standing this side here and looking at this curve in the mirror, you will end up seeing that it's going to be something of that kind here. So this one here as a whole is the inverse of this function here. But this side, because it's positive, so you'll find out this portion here is this positive, the square root of x. This side is negative, you'll find out you have a negative square root of x. And if I pick a value here, x is equal to 5, it's going to have that output there, which is positive square root of 5. And also it's going to have that output here, which is minus square root of 5. Hence this one, it's not a function because it has two outputs, or the vertical line test fails to prove that it is a function. So this is an inverse, and this is how you actually find the inverse or the reflection of this given function by the line y is equal to x. But now let's look at some of the other important reflections. Okay, let me first give you another example here to see what do we mean by an inverse. If, let's say, I am saying find the inverse of the function y is equal to x cubed. Of course, your inverse would be, the first step, we want to interchange x and y, so you will end up having the inverse. Let me look into this. You will end up having x is equal to y to the power 3, and then you want to solve for y. When you're solving for y or making y the subject of the formula, you'll find out you will end up having the cube root of x. And whenever this exponent is an odd number, which means we have 3, 5, 7, 9, 11, and so forth, you don't end up with a plus or minus. You only end up with a plus or minus if this number is 2, 4, 6, 8, 10. That's what you end up having. So you will end up, and this inverse here, which is usually written as the inverse of x is the same as 3 square root x, is actually a function in this case. That's how you find the inverse. Now let's talk about the exponential function now. Exponential function. We talked about exponential functions back there in the previous videos, and we said that an exponential function is a function f of x which is equal to a to the power x, where a is greater than 1. So this is a constant, it is greater than 1. It's not it's greater than 0. It's not a negative number, and it's not 0, because 0 raised to something here will end up having a 0 or undefined if x is 0. So this is an exponential function. Once this a is negative, it is not an exponential function. And of course, the domain of this, x is an element of real numbers. We can plug in anything. So we ended up saying that the plot of this is not straightforward. We have two of them depending on the value of a. We cannot just say all the exponential functions look like this. It depends on a. So we end up having two plots here, and the first one is for when a is greater than a 1. So let me remove that. We have a y this side, we have an x this side, we have a y this side, we have an x this side. So the first one, it goes like this. And of course, always, all these exponential functions, they pass through that point, which is 1 here. And then this one is when a is greater than a 1. So this is y is equal to a to the exponent x. And if this one is not, and of course it does not touch the x-axis here, so it goes that side forever, and this becomes an asymptote. And now when you look into this side here, we have a is less than 1 but is greater than 0, because if it's less than 0, it's not an exponential function. Of course, it's gonna have to pass through that point, and it doesn't have to touch the x-axis. So that one, it keeps decreasing like this, right? And you can see that this one is a decay, and this one here is growth, right? When you look into these two curves, you will find out that if I am looking for an inverse, I have to draw a line here, which is y is equal to x, and act as a mirror there. This point here, which is a y-intercept, it will become an x-intercept there. This horizontal asymptote, it will become a vertical asymptote. This one is when y is equal to 0, it will become a vertical asymptote at x is equal to 0. So we have a vertical asymptote there. So this curve is not supposed to touch this vertical asymptote, and is supposed to go on like that. And of course, this one here, we interchanged x and y, so x comes down and y goes up. So we end up having x is equal to a to the exponent y. And then this side, of course, we also draw a line here, which is y is equal to x, and this is the mirror. And you can see that whatever this curve is, it has to pass through that point here. If this was 1, this will be 1. And this horizontal asymptote becomes vertical asymptote. When y is equal to 0, we have a vertical horizontal asymptote. So at x is equal to 0, we should have a vertical asymptote. So here, you will end up seeing the curve actually is not going to touch this asymptote, because it's like this. So it's not going to touch it, but it's going to pass through 1, and it's going to go on like that. So we have these two curves, and this of course is x is equal to a to the exponent y. We talked about those two things, and we talked about their domains. And if you look carefully in these two functions, you will find out that this function here, because y is up there, and this function here, because y is up there, you will find out it is only defined when x is greater than 0, and it is only defined when x is greater than 0. So the domain of this new function is when x is greater than 0. Let's go back to the definition of this exponential function. An exponential function is written in this exponential form, that you have a constant, right? This constant here is greater than 0. So this constant is greater than 0. And it is raised to an independent variable. Independent means the variable that is controlled, or the variable that we keep changing. And then this variable here is the x values. We usually represent the independent variable along the x-axis or along the horizontal axis. That is why x is here. And then here we have the dependent variable. Dependent does not go like this. We have dependent. Yeah, dependent variable this side. But if you look into this curve here, you'll find out now we have a dependent variable this side and independent independent variable this side and independent. You'll find out that the independent variable is this side, and that side here is the dependent variable. So this one is not an exponential function, because for an exponential function, the independent variable should be an exponent. So not exponential function. So we need to have a name for this particular function. That's when we started to define logarithmic functions. Right. The function x is equal to a to the exponent y is a logarithmic function. Logarithmic function. So it is a logarithmic function. Take note that this a here is greater than 0. So this a here. So because this confuses a lot of people, because it is written in an exponential form, we want to have our definition that is actually saying this is a logarithmic function. That is why we define a function that brings this y down and actually rewrite this whole thing, and we start to see x as an independent variable, and we say y is equal to log base a of x. So this function here and this function here is one and the same thing. They are both logarithmic function. They have the same values. It's just that this one makes y the subject of the formula, this one does not. That is why we usually have this. So the domain of this function is the domain of that function. That is always defined when x is greater than is 0, this function here. And this base here must always be greater than is 0. So that's what a logarithmic function look like. If the base is less than 1 and greater than 0, the logarithmic function looks like this. And if it is greater than 1, it looks like this. And now that we talked about this particular function here now, which is a logarithmic function, what are the rules of this function? Before we talk about the rules, I want to also introduce another definition here. If the base a is equal to e, where e is the Euler's number or Nepler's constant, which is approximately 2.718 blah blah blah. In a calculator, it is here, is this number here. So you press, remember that when you wanted to find pi, we used to press shift and then you press pi, and then pi comes out, and you can try and keep changing pi to be either you approximate it or you keep it as pi. Pi is close to this number. But if you press this alpha here and then you press there, you end up seeing an e, and e is approximately that number there. So if the base here is e, then the function y is equal to log e of x. We define it as ln of x. This is L, the natural logarithmic function. Natural because this e is a natural constant, and this ln is here in a calculator, right? Another thing you will have to notice here is that if you take ln of e, you're supposed to get a nice thing as a 1. So ln of e is equal to 1. That's one of the basic properties that we usually like to work with. Now let's look at this y ln of e is equal to a 1. Whenever you have let's first talk about the laws of logarithm. Laws of logarithms. We proved them when we were doing these laws in one of the previous videos we had, but I'm just going to mention them without proving them here. If I have log a of the product of x and y, I have log a of x is supposed to be this is supposed to be equal to the sum of the logs of x and also the log of y, but the basis is still the same, but I split these two. And then the second one is if I take the log of a of x divided by y, I'm supposed to get a difference of this. Take note that the numerator is the one that goes first, and then you subtract the log a of the denominator. So log base a of that. And then we have the third one, which says if I have a log a of x to the power b, I can always bring the exponent down, b log a of x. And if I have log a of x, this is the same as just log x divided by log a. Now, if you look in a calculator, you'll find out we have a log there that doesn't have a base. And the one that have a base, you always see it as log, and then you have a base there, and then you have a number going there. So here you can either just have log x or log a. What that's supposed to mean, it means that we can always place any base here as long it is greater than a 0. We will get the same thing as that. So that's what I want you to know, this basic laws. Now you will see that if I am saying I want you to find ln of e. Ln of e is the same as, by definition, ln is log e, and then what was inside is here. This is the same as if I'm using this rule here, you will find out that I will end up having log b of, I take the number which was inside here it is e, and then I divide it by log, and then here I will have a b, and then I take this number here which is e, I plug it inside. But this and that is the same thing, and then you end up having a 1. That's where that 1 came about. We used this law here. But nonetheless, we know the log, we know the exponential. In most cases, it is easy to work with exponential function of this kind, y is equal to some e raised to x, compared to working with an exponential like this, where a is not e to the power x. Why is that so? It's because, like I said, this one you'll find out that if you want to find the slope of this curve at any point, you'll find out that the slope is still the same as that. That is why it is good to work with this compared with that, because the slope of this, that's something else, but for this one it is easy. And if I just add a k there, the slope will be k times the original function. That's why it is always nice to change sometimes from this base to those bases, right? So now we're talking about want us to talk about the conversion of bases. Conversion of bases. Sometimes you have y is equal to a to x, and you want to convert it maybe to y is equal to b to some other thing like b to the power x. Let me first talk about this, and we want a different base. Let me just talk about this. One reason will be, when you're dealing with this base, there is no data or there is no information that is actually known that can be linked to other people's work that have this base. But when we are talking about a different base, you will find out maybe that there is some work of someone else who was working either sometimes probability, sometimes energy when it comes to chemistry, that has to do with a different base. Now you want to see if the results you have that have this base here, there is any link with the work that is found that has to do with that base here. So that's one of the reasons why you will want to change from this base to that base, but you still have an exponential form. Another way is sometimes this base is going to complicate your calculations, but that base is going to make your calculation easier. That's why you end up converting from one base to another base, right? So how do we end up converting one base to another? Suppose you have this function and you want a different base. If I am saying now I'm just gonna place here, I wanted to rewrite this as b to the power x. If I have x and just x there, and I have this b will just be a. And if I am placing a k here, now I have base a here, I don't have base here, I have k times some base raised to something. I don't want that. I just want to have a different base. So this k cannot be in front of it. But if I place a k somewhere there, you will find out that now I don't have this an exponential function, which is some base raised to an independent variable. I have now a base raised to an independent variable plus something. I don't want to have plus something. I want to have base raised to something. So we end up not placing that k there. We place a k somewhere there. So when we end up having this k there, now the question will be, what is the value of k? What is the value of k such that this exponential function is written in that format, but this b is different from a? So how do we end up doing that? Here we wanted to have a to the power x equal to b to the power kx. And you know that this is the same as just b to the power k x. And of course, it is the same as b to the power x raised to k, because if you multiply x and k, you're still going to get kx. If you multiply k and x, you're still going to get the same thing. So we either have this and that. Why do we change this to that or that in the first place? It's because this side I have a base raised to k, to x. I want this side not to have a base raised to kx. I want to have some base raised to x alone. So this one is raised to x, but k is outside. I don't really want that. That is why we're changing it to this format here. In other words, we have a to the power x is equal to b k all to the power x. So we have this nice thing here. I have an x here, I have an x there. X and x are the same, which means that because this is equal to that, I have a is equal to b to the power k. So what will be the value of k here? If you go back to what we were trying to explain here, we said that x is equal to a to the power y is the same as y is equal to log a to the power x. So these two things are the same. In other words, whenever I have some number here is equal to some base raised to an exponent, this thing here is the same as saying I have an exponent here. Exponent is equal to log base and number inside. So these two things are equivalent, or these two things are the same. So I wanted to bring this exponent down, and then I have a log. Of course, the base is going to be b, and then a is the number, so it goes inside. So I have k is equal to that. Which means now, if I want to rewrite y is equal to a to the power x in this form b to the power kx, then my y, which is equal to a to the power ax, is going to be equal to b, and then the value of this k here is going to be log b, and then I have a inside, and then I have an x there. Now let's look into this. Whenever you have this b, this b must also be the base of that log, and then this a that was here must be inside here, so that this b and that can actually tell you that I can get this a to the power x from this. Let me make a simple example on the side here. What do I mean? And the use of these laws. If I have b to the power log b a times x, which is that, I can always place that x that side. It doesn't matter, this and that is the same because it's multiplication there, so I can put it first here. And if you look into this, this is the same as b log base b, and then I have an a there. I'm going to place some space here. If you look into this law here that we have, whenever I have a b, I can always bring it down. I can always bring it down to get that. And from here, I can always take this b and make it an exponent to get that. So this and that are equal. But in this case here, we have an x in front, so I have an x there. So x can be an exponent. So take a look here. If I have a to the power x, this is the same as b log b a to the power x. So that's also something I want you to take a look at, that this b raised to log b, they cancel out, and then this and that you will be left with. So that's something that I just wanted to point out, but this is how you would end up converting these things here. Now let's take some of the examples and see if we can use this formula here to solve them. If you look into this example here, the question is, rewrite f of x is equal to 2x now with a different base 3. Let me see if I can try and rewrite this. So I have copied this. I have rewrite this with base 3, rewrite this with base 3, rewrite this with base e, rewrite this with base 8, rewrite this with base 3. Now, what I actually wanted to do here to solve this is not that hard. We just use the same procedure we're using here, but now we are converting to find the base e. One way to do it, you can just use the formula that we derive right away, or you can just keep practicing. What you need to do, practice this, and then you can pause the video, and then you start with your you start by doing these exercises, and then later you check your answers. That's what you can do to practice. But let us do this. So f of x, this is the solution here, is equal to 2 to the power x. And now this whole thing here is very simple. I wanted to write with the base 3. So I'm going to place this 3 here. I'm going to place a log base 3 so that this and that, it cancels out. And then I'm going to place these 2x there so that these 2 can cancel out, and then I can get that there. But if you look carefully into this, I can just take the x in front there. So I will end up having 3 raised to x log 3 of 2. And if you look into this, I can just say 3 log 3 2 times x. So this is how you can end up changing this whole thing. It's very straightforward and very easy to do. You have that. And the same thing here, I have my f of x, which is equal to 2 to the power x, is equal to, I want base 3 here. Of course, I am going to have 3 raised to log. I want to cancel this 3 that I've placed here. I have a 3 there, and then I will have, no, I wanted e here. So this one was supposed to be e to the power x. So I have e to the power x there. And if you look into this, I can always bring this in for the exponent in front. So I will have 3 raised to x log 3e. And then if you look into this, this is the same as 3 raised to log 3e and then times x. So you can have this or that. And then here, if you look into this one, also with base e, I can have f of x is equal to 3 to the power x, and now I want to have e, and then I want log e so that it will cancel out, and I will have this 3 to the power x. This is the same as I can bring the x inside, so I'll have e raised to x times log e of 3 here. So I bring that x there. And then I can work my way out and say you have log e raised to log e of 3 times x. But now you know that whenever you have log e means ln. So I can have e raised to ln of 3x. So that's our conversion here. We can even check it with a calculator that what is this going to be? What is log this here? So you can see that whatever that value will be will actually bring us to that point there. So if let's say I'm saying 3 raised to, I'm going to look for this log, and then I'm going to look at this piece here. So I have 3 and then I have a 2 inside. You will find out that this is 2. So this whole thing here is 32, and then we raise to x. So all of them are actually giving us the same thing. And if you look at, let's say I'm having now an e, and then I raise it to ln of, I'm looking at this one here, ln 3, and then you will see that it's supposed to give us a 3. So you'll find out you get a 3, which is this 3 over here, and then that x is there. Now, I want us to take a look at these two here. I want to rewrite this with base 8. You will find out now I have f of x, which is equal to 2 to the power 3 of x. And of course, this is the same as 2 to the power 3 times x. 3 times 3 will get that. And if you look into this, this is 2 times 2, which is 4, times 2, which is 8. So this is going to be 8 to the power x. So that's how easy this thing is. And when it comes to this one here, you will find out if I have f of x is equal to 81x, this is the same as, this is going to be 9 squared in place of 81 to the power x. And if you look into this, you can simplify and say 9 to the power 2x. I'm multiplying these two, and 9 is the same as 3 squared raised to 2x. And if you look into that, this will be the same as 3 raised to 4x. And you can see you have a base 3, which we're looking for, and you have base 8, which is what we're looking for. But if you look carefully into this, you'll find out when you are dealing with this change of bases, you will find out that that's not what you were looking for. You want to use this understanding of a log and see if you can actually get this using this log there. Remember, I said this is the same as, I want base 8, so I'm going to have an 8 there, and then I want to have a log, and because of this 8, I want to have log base 8 to cancel with that, and then I can keep 2 to the power 3x. Right. And if you look into this carefully, you will find out that this thing that is inside, I'm going to still have an 8, I'm going to have a log, I have an 8 down there, and here, this is the same as 2 to the power 3 all raised to x. So I have this thing here which is raised to x, because if I multiply these two, I'll get 3x. And now, this x, which is an exponent, it can always go down. So I will have an 8 raised to x times log 8. And if you look at 2 to the power 3, it is the same as 8, right? So if you have this, we have log 8 and 8 there, what will actually happen? Let me just open a window somewhere here. Log 8 of 8 here is the same as log, I'm going to take this 8 here and then plug it inside, and then I'm going to divide by log the base here, but still the same as 8. I can place any base here. Either I leave it like this and assume base 10, because if you have a log here, just log, it means that the base is 10. But I can always put any base that is greater than 0 here. So this and that will actually give you a 1. So log base 8 of 8 is equal to 1. So you end up having 8 to the power x, as we did before. And the same thing here, you will find out that whenever you have f of x is equal to, I want base 3, 81 to the power x. I want base 3, so I want to have 3, and then I want to have log 3, so that these two cancel out, and I want to have 81 raised to x there. This is going to be the same as 3 log 3, but this x I want to bring it in front, so I will be left with 81 here, and I will have an x there. And if you look carefully into this, I will end up having 3, but this x can be this side, and we have log 3 3, and then you have 81, and then times x there. But if you look into this 81, you'll find out that we can actually work it and say we're going to have 3 log 3, and then we're going to have 81 is the same as 3 times 3 is 9. 9 times 3 is 27. 27 times 3, you end up having 81. So we have 3 to the power 4, and then have times x. And whenever you have an exponent inside the log, I can always bring it up front. So we'll end up having a 3 raised to 4 log 3, and then you have 3 times an x. Now, I have this number and that number there. They are equal, so this whole thing will go to 1. But if you want to check it out, you can see that log 3, it is the same as log base b 3, and then all divided by log base b 3. This and that is the same, it cancels out, and then you're left with 1. So this will be 1, and then you end up having 3 to the power 4x. And then that's how we end up dealing with this problem, and we are done.